Mr. Tickner, and this is a video to take you through the bits of the revision list so you are aware of what's going to come up in the assessment, and so you can watch the bits that are, if there's anything you need a reminder on. So this is the revision list that you've got, and I'm sort of breaking it into 3 different chunks which I'll kind of timestamp. The first is this stuff here, which is all about drawing rays of light and the law of reflection and how we see things and look at things in mirrors. The second sort of topic we did was on the topic of refraction, where we looked at light bending as it went from air into a different medium. And the third one is about colour. Okay, so I'm going to tell you 3 little bits on all of these in turn. So the first bit, let's take this first up, how we see things. Okay, so we've got drawing rays of light, luminous, non-luminous, shadows, reflection, and mirrors. Okay, and we're only ever going to deal with sort of flat mirrors. So let's do this one, and let's go with this colour. So let's start our section 1. Okay, rays of light. Okay, so let's start with the biggest object in the sky that you can see, the sun. Okay. The sun is an example of what we call a luminous. Let's actually label it the sun. It's a luminous object. The fact that it's luminous means that it's giving off its own rays of light. So if you want to look at the sun, which I do not advise you do directly, if you have someone here and they're looking at the sun, how will they get to see the sun? Well, rays of light are going to come straight off the sun to that person. And the key thing is that whenever we draw rays of light, we use a ruler. Okay, so we have a sun, we have the sun, we connect it up with a ruler. Here's a ray of light, and there we go. And the key is that is going from the sun to the person, so we draw an arrow that way. And there we go. That's how you see a luminous object. What about a non-luminous object? So let's imagine that this person is standing near a very weirdly shaped tree. So let's get a nice green colour. There's our tree. Now a tree is non-luminous. Okay, so this is non-luminous, meaning that we don't get light from it directly. Light has to come from a luminous source and reflect off it. And so if we wanted to see how do we see the tree, or we might have a ray of light that is doing something a little bit like this. So actually let's have it going a little bit lower. Let's do that. So we have a ray of light coming from the sun. It's all fine and lovely. Going in. Oh, come on. And then we're going to reflect that off. Again using a straight line to the person. And there we go. Quite straightforward, but that is how we draw things. Always remember to have your arrows. Always remember to use a straight line. Okay. So how are shadows formed? Okay. So next thing we want to think about is how is a shadow formed. So let's start with a sort of an object. Let's try and see if I can draw a torch. This is my effort to draw a torch. And it's going to be giving off light, so let's have a sort of excellent. That's as good as I'm going to get today. There we go. There's a torch, which is a luminous object, and we're going to put a person in the way, a person who's going to be sort of here, and they are standing in front of some kind of a wall. Oop, go away. Okay. So how does the shadow formed on this? Oh dear, he's got the wrong coloured eyes. That was not what I intended to do. Well, he does him. Right, okay, so with this, what we need to do is we have to say, well, any of the light from the torch, there has to be a region where this thing can't go. And the way that we sort of identify this is by thinking, okay, what is the region at which this light can't get in? So we draw a line from the top of this person's head. So let's do our first line in yellow. Okay. From there. And from the other outside, from the bottom of the torch, oh, zooming in quite a lot there. It's not one to go at an angle. So we can skip at the bottom of this person. Okay, and what there is here, okay, so there is no straight line that I can draw with a ruler inside this area where my torch can hit the wall. So nowhere inside this top bit to this bottom bit, there is nothing I can do, okay, there's no line I can draw that can hit the wall, okay, so this is the part of the wall that's going to be in shadow. So the shadow is going to appear here. Okay. In terms of like astronomical things, and I know people looked at in terms of it being the you know sort of to do with eclipses and the shadow of the Earth or shadow of astronomical objects. It has a formal term. It's called an umbra. But the way you find where the umbra is exactly in this. You draw a straight line from the top of the torch or top of the object given the light. The part that hits the top of the object and keep a straight line. And do the same at the bottom, and this area here, no light can get into here, okay, and that's how a shadow is formed. Okay, state the law of reflection and draw a ray diagram showing reflection with the normal and the angles and so on. So this is kind of how we can see things in mirrors and so on. So I have, and the standard way of doing this is we've always put a flat mirror. So a mirror is always I don't know what, I've got a ruler and I didn't draw a straight line. That was very, very careless of me. Let's rub that out. Let's take this here and let's draw a flat mirror. So this is the law of reflection. So we have a surface. Now mirrors are smooth and shiny. If you want to ever show which side of the mirror is the back, you have these little lines and this shows that shows the back of the mirror and this side is the front. And what we have is always a line will come in. Oop, dear. So we'll have a ray of light coming in. So let's say we've got this one coming in. Let's use a red pen for this. Okay. And this ray that's coming in is called the incident ray. That's kind of the formal term for the thing that's going in. Okay, that's always the incident ray thing going in. So that ray is going to reflect, and the ray is going to reflect according to the law of reflection. Okay, we need to measure an angle. So the angles we need to draw are, we first need to draw a thing called the normal. Now the normal, not the easiest thing to control, I'm going to try and learn this. So the normal is a 90-degree line, and it's always 90 degrees. It's where your incident ray hits, and it's at 90 degrees the thing you've hit. So this line right here, and let's do this in, it's such an important thing, let's do it in a rainbow pen. Oh no, let's not do that because that's too thin. Let's do it if we do it really thin. Oh, well, let's do it. That one? No. Oh, okay, so that's the one we want. Rainbow pen, and let's do it really thin. This is often a dashed line. Not sure whether this was the wisest choice. Yeah, let's go with it. Okay, this is called the normal. Okay, normal just literally means 90 degrees. Okay, it's at 90 degrees, not to the ray, but to the mirror. Okay, so no matter what it hits, that's where 90 degrees to. And so what we'd have is we'd have a, we measure an angle, and we measure the angle of incidence, which is this one. We always measure to the normal, and that has a little letter I for it, so that's the angle of incidence. Incident ray, angle of incidence. Now, I don't have a protractor on this wonderful piece of thing, but I do know that I measured this as an angle going in of 32 degrees, I believe. So there we go. So that's 32 degrees, which would mean that this is 58 degrees because it's 90 minus that. So this angle here is 58 degrees. Now what that means is that my reflected ray comes out with exactly the same, at the same angle of incidence. So let's do a blue line. Have this going here. This is our reflected ray. And this is also a little R for this. And this will also be 58 degrees. And this is the law of reflection, okay? That the angle of incidence is equal to the angle of reflection, okay? It doesn't matter what kind of orientation your mirror is at, or this is the way you do it every single time. So, but the law of reflection so the angle of incidence equals the angle of reflection. And that's the reflection. Okay. Now for someone who's viewing it, so if you've got a person who is kind of here, okay, they see the reflector ray. And as far as we always think that rays of light come in straight lines. So we have no real way of knowing whether there is a mirror there or not. So as far as your brain is concerned, where the ray actually came from continues to be along this straight line. So if I just get this up to phase 2, and we continue that line back, and in this way, so what we do is continue with the dashed line. Okay, we would think that place the images, there's an image out here, it's called a virtual image, we think it's come from over here. So this is why we see things in the mirror, is because that's where our brain assumes that my rays of light has come from. This dashed line is called a virtual ray, nothing's really there. Okay, so that's section 1. Let's move on to section 2, which is refraction. Okay, so okay, so refraction as a property occurs, okay, whenever a ray of light passes from one thing into another. So it's got to pass through a transparent material, and it changes speed. Okay, so as a sort of formal definition, okay, refraction is when a ray of light passes from one medium, okay, so medium is the thing that things travel through, to another, changing speed and direction. Okay, so basically there's always a change of speed, and the classic thing that we did, or that you do as in a practical, is you fire rays of light into blocks, and so this is kind of what you get. I'm just going to sketch this. So we could have air, and the block that you would have used in the lab was perspex, and in perspex, because it's denser, light travels slower in this than it does in this. Okay, for reference, it travels at 300 million meters per second in air, it only travels at 200 million meters per second in pressure. Still pretty fast, but there we go. And what we get here is we end up with refraction. And whilst there's a law of refraction, that is not something that you need to know in year 8. It's something you'll meet later on in your science career. So we have our incident ray coming in, and we have our, let's get our ruler for our normal. So let's draw our normal. Let's draw it in a normal pen this time. Okay, so this is the normal. This is our incident ray. Got my arrows going on here. And this again is my angle of incidence. And then what happens inside? Well, in perspex it travels slower, and so we get a change of speed and a change of direction. Might look like that. And then on the way out, we're going to get back to so I'm going to get this coming out here again. And draw our normal again. So this is the path of a ray of light through a perspex block. Okay, so what we have here, okay, let's deal with, just zoom in so we only think about what's going on when we go into the block. Go into the block, we slow down and we bend toward the normal. Okay, so this is when we slow down, okay, we've gone to something denser, we've slowed down, and this angle, the angle of refraction, is smaller than the angle of incidence, and this is bending towards the normal. Okay, so you're going here, then you go here, and kind of the idea is that you're now closer to the normal than you were. Okay, so this is what happens when you going in. So going in, or slowing down, angular refraction smaller, bends towards the normal. When we come out, the opposite happens. So when we come out of something, when we go from perspex back into air again, well, this sort of the opposite happens. We speed up and we move, and we bend away from the normal. Okay, so this angle is now bigger. But at any point, you're only interested in what happens either side of the boundary. Okay. Now, there is one very special case, which is what happens if you are already traveling along the normal. So let's say you are going along in this direction. That's a pretty nice straight line. So you're already on the normal, because the normal is literally there. Well, in this case, you will still slow down, but you don't change your direction, you just carry on in a straight line. Okay, and so this is refraction. Okay, this is the three things that you kind of need to know about refraction. What happens when you go in or when you slow down? Your angle becomes smaller and you bend towards. What happens when you come out? You speed up and you bend away. And then just recognizing what happens if you're traveling in a straight along the normal anyway. Well, you still slow down, but you don't change direction. Okay, so that is something that's worth just saying. You know, so key things. So if the light, so going from, so we go from a less dense, say air, to more dense, say perspex. I'm going to write it in a different colour actually. So we have light slows down and bends towards the normal. If we are going from more dense, so perspex, to less dense. So air, we have light speeds up and bends away from the normal. Okay, and just the special case of if you are traveling along the normal, okay, there is a change of speed only. Okay, so no change in direction. Cool, right, so that is refraction. What is the kind of key thing that we would do with it is to say, okay, well, when you look underwater, things aren't always where they appear to be. So if we are to look at something, so I've got sort of water, I've got a water line, so it's just water down here. Okay, and let's say we're looking at something underwater, say we are looking at a fish. Okay, and we are, let's say we are, so we are here. Okay, if we are to try and think, well, where does this fish? This is where the fish really is. Okay, it's really here. But where does it appear to be to our eyes? Well, we are going to have to deal with the fact that there is refraction. Okay, because what is going to happen is the light will not travel in a straight line from us to the fish. Okay, this isn't going to happen. We're not going to see the fish exactly there because there's a change of medium, so there's a change of speed. Okay, so we're going to see things in a slightly incorrect way. And so a possible path, depending on sort of the bend, would be something like this, that the light from the fish comes up, okay, comes to here. And then we would have the normal, so let's draw the normal and just make sure this is absolutely clear as to what we're saying is going on. There's our normal. Okay, and because our ray of light is traveling from a more dense, where it's slow, to less dense, where it's fast, it's going to bend away from the normal, which is then going to take it towards our eyes. So something like this. So we can say, yeah, let's carry on with, let's do a yellow this time. So we're going to see a ray of light doing that. And so according to this person, the fish is actually not down here, but is sort of somewhere there. Okay. Okay, so this, turn this up a bit. So this right here is the image of fish we see. This right here, that's the real fish. Okay, so that's where it really is. But if we were to trust our eyes, we see it in the wrong place. Okay, so that's the kind of the case of refraction of something going from water. Why don't we see it where it really is? Cool. So that's that one. Last section, color. Right. Okay. Still with color. Let's use our rainbow pen to write this title. Okay. So color. Okay. Key ideas. One. Okay. Is that white light is made from the color. color spectrum, which is in turn red, orange, yellow, green, blue, indigo, and violet. Okay, so white light is made up from all these colors, and black is an absence of light. Okay, so in order to see, for example, this is a white sort of like image on here. What your computer screen is doing to tell us this is to say, right, okay, we're going to send enough light at you that you will think this is white, and actually we're not going to send any light from any other part of the screen that's currently got anything in it. But your computer screen is actually very clever, because actually what it does is it just mimics it by using some red, some green, and some blue. And by combining it, it can trick you into seeing white light. Now, how did we discover this? The person who discovered it, Isaac Newton, doing a wonderful experiment involving a prism. So there is our prism, which is a triangle, and he fired in. Should already be using a ruler, but this is what this diagram looks a little bit fiddly. Oh, that's nice. So he fired white light into a prism. Okay. And what he found, I only ever do this with red and with blue, so with different ends of the color spectrum. But essentially what he found is that these different colors of light would refract, but refract at different amounts. Let's use purple. So you go right to the violet end. So we have red, and then we have violet at this end, and in between we have the whole color spectrum. So by using a prism, we can split the light because we refract it here, we refract it here, and this whole process is called dispersion. Okay, so this is the dispersion. With a prism. Okay, and this is where you see a rainbow on the screen, so you get Roy G. Biv in there. So red, orange, yellow, green, blue, indigo, and violet. Okay, red being refracted the least, violet being refracted the most. And that's how we sort of, so that's the key sort of idea. Right, okay, so color spectrum, we've got the spectrum of light. Right, so your computer screen doesn't have to send out all of these things. It doesn't have to send out everything. If you actually zoom all the way into any computer screen or TVs and things, actually, you will find red, you will find a green, and you will find a blue. So these are it's sub-pixels within the actual computer screen. And it turns out that vision is sort of based on cells in your eye that kind of detect red, kind of detect green, and kind of detect blue. It's a bit more complicated than that. But by sending different amounts of each of these color at you, or in fact all three, we can actually trick you into seeing all of the colors, which is pretty cool that we can do that. And so vision, light, is based on, so when we want to mimic sort of vision, we use the three primary colors of light. So to create color in screens, we use three primary colors. Red, green, and blue. And I can't spell blue, that was embarrassing. Blue is what we want. And what we have is, am I going to be able to draw a nice little shape? I am. No, okay. So, and the way this often is drawn is with this kind of weird sort of Venn diagram of colour. So I'm going to draw a red circle. So vaguely fill it in. I'm going to draw a blue circle. And I'm going to draw a green circle. And the red, the green, and the blue form the primary colours. I need to just delete a little bit there. I'm going to zoom in so I can have this in. And when your eye detects multiple ones, well, we see things. If you purely see blue light, you see blue. If you purely see red light, you see red. If you purely get some green light, you see green. So that's what you're seeing there. In the overlaps, however, if we send all three to you, you see white. So if you get sort of some red, some green, and some blue, that gives you white. Okay, and then it becomes a question of, well, what happens when you get two colours? Well, if you get red and green together, you will see yellow. Okay, don't need to do that. So you will see yellow. Why will you see yellow? You see yellow because yellow is kind of yellow sort of orange. These are the colours you see. These are the colours that are between red and green on the colour spectrum. So that's what you see. And if I give you slightly more red than green, then you kind of see orange. So that's the thing we get. If we overlap blue and green, although it's not in the colour spectrum, it's there if you kind of spread the whole thing out enough. You will get this colour, which is called cyan. Should really probably be labelling these things. We have yellow. Okay. And then if you overlap red and blue, you get a weird colour called magenta. Okay. And interestingly, magenta is a kind of entirely invented colour by your brain, because actually if you look at the colour spectrum, between red and blue is green. So actually your brain, we've actually developed the kind of pinky color to kind of like say, okay, this is what I think I'm seeing when I get red and blue, to kind of allow you to differentiate things. It's a very clever thing. So what we have are the three primary colors, red, green, and blue. And when they overlap, we have the three secondary colors, which are yellow, cyan, and magenta. And these are all formed of color combination. So yellow is red plus green, cyan is green plus blue, magenta is red plus blue. And this is basically all the things we can use to trick your vision. Okay, this is how we can trick you into seeing pretty much anything. So this is important because if we let's say we illuminate an object, okay, when we illuminate an object, objects have a particular color, and they will reflect that light so long as it's there to be reflected. Okay, so if you have a colored object, okay, let's say we have a green, let's say we've got a green object, okay, and we want to know what color is this thing in various things. Well, if we illuminate it with white light, okay, white light, well, that's great. There is green in white light because it's there. Okay, this circle is there. There is some green there, so we'll reflect that green, and we're going to be able to see it as green. Fantastic. Okay, protected object, however, and we illuminate it with, let's say, green light. Again, that's fine because there's green light there, so green will reflect. If we take a green object and we shine red light on it, well, there we have a problem. Here, there is no, red light has no green in it, which means because there's no green in it, there is no green to be reflected, so we do not see this object. Okay, there is no reflection. The red is absorbed. It is going to appear black. Okay, in a perfect world, or grey. It's just not going to have a color because there's no green light to be reflected by this object. If we shine, so let's take our final one. If we shine a secondary color which has green in it, so let's say we shine cyan on it. Okay, cyan, if we check it, is made from green and blue. Because it's cyan, that means there is some green there, and what that means is that we will reflect some green light and it will appear green. So every single time if there's a green light, will appear green, will appear green, will appear green. It's all about what colors are going in and therefore what colors can come out of an object. And so you can apply this to any of these things. Okay? So that's what we have with those things. If you have an object which is, say, yellow, okay, that's an interesting object because if we remember, yellow equals red plus green. Okay, and this is where it becomes a little bit. Okay? So again, if we start through it, let's shine some white on it. Okay, so we have white light. White light has red light in it and has green light in it. Great, will reflect yellow. Boom, fantastic. We'll think it's yellow. If we shine on our yellow object, and let's shine blue light on it. Okay, let's shine blue. Well, blue light, no, there's no yellow there, so we have nothing. It's going to appear black. Next thing, however, let's shine green. What color is it going to appear if we shine some green light on the object? Okay. Well, in this case, we've got green light coming in. That's good. We match up with the greenness of the yellow object. So that will reflect. Fantastic. There's no there's no red to reflect. So in this case, what we're actually going to see here is we're going to see the object as being green, even though it is yellow, which is a bit weird, but there we go. That's how we see these things. So again, all of these things you've got to remember, or you've got to think, is say what colors are going in and what color can the object reflect. And sometimes there's multiple, so that, and so that is what you're going to get. Because obviously with a yellow object, this actually also means that if you shine, we shine a red light on it, okay, so let's shine red onto the thing. Well, a yellow object can reflect red, so off it goes, and it would appear red. So sometimes your vision can be tricked based on what things appear. Final thing is filters. Okay, so and to be honest, this is kind of how we make these individual colors in the first place. A filter is basically a sheet that absorbs all colors except its own, which it lets through. And looks like I can't spell it. Okay, so what does that mean? Okay, so let's say I have some white light and I have a red filter. Okay, I can think of white light as being made up of red, green, and blue. Okay, red, green, and blue. It's a red filter, which means that my blue gets absorbed, my green gets absorbed, but my red light gets through. And so on this side of it, I only have red light, which is then what I could do if I wanted to create one of these weird situations here. Similarly, let's say I've got some yellow light coming through. Okay, so I've got some yellow light, and I have a green filter. Okay, what am I going to see on the other side? Well, yellow light is made up of red light, and it's made up of green light. I've got a green filter. Green is going to absorb red. It's going to let through green. So therefore, I have that coming through, which is lovely. Okay. The secondary filters work exactly the same way. It's just they're letting through two colors of light. So let's say I have, let's say I've got some blue light, and let's say I've got a cyan filter. Okay, blue light is purely blue. Cyan will let through green or blue, which is nice. So it's going to let through either green or blue. And what that means is that my blue light can happily get through, and I'm going to still see the thing as being blue. Okay, so again, every single time with these, you just have to take it through in stages, always thinking, what have I got going in? What does my thing let through? Or in the case of objects reflecting, what do they absorb? What do they reflect? And therefore, what am I going to see on the other side? If you place a green filter, say after this situation, okay, and so we now have this situation, let's say we have red, then we have green. Well, we're not going to see anything on this side because we blocked the green light because of the red filter, and then we blocked the red filter because of the green filter, so we see nothing. And we're going to see black, or we're going to see darkness, we're going to see an absence of light. And that is colour. And that is the whole of the Year 8 topic. And I hope the various bits of that have been helpful.